So, yes, I'm Paul Walmsley, and I want to talk about a few specific techniques for experimental repeatability and robustness that is really kind of quite geared to software projects in particular. And to give you just a bit of background on myself, I started out my academic background with my PhD in Bayesian musical signal modelling a number of years ago, and from then I went to Sibelius, which is now part of Avid. I've worked on the Sibelius product for the last 12 years, and one of my daily duties is maintaining Hudson on a day-to-day basis as well. So I'm wanting to try and give a bit of a feel of how some of the techniques that are very common to software development can help you improve the reproducibility of the things that you do in your research life. So, I think, as Mark's already alluded to, the reason why reproducibility is important is because other people rely on it. It's pretty much a basic tenet of scientific research, really. People need to be able to reproduce your work in order to then go and compare it to something else and develop their own things on top of it. If you're having to work with other people, they need to be able to reproduce your work as well, so that what works on your machine works on mine. If you're wanting to publicise it, write it up in paper and not end up in that journal, then it needs to be reproducible. Someone else needs to be able to see it working. And if you're wanting to commercialise it, take it round to a company to sell it, they're not going to be very interested if it doesn't work for them in the demo. So I want to talk about three particular techniques that we can use. One of them is how we can design experiments, and then how we can apply version control to take control of the software elements of it. And I'm going to talk very, very briefly as well about unit testing as well, how this can really improve your robustness. So a typical kind of case study of something that you might experience is that you work for 6 months on your research, and by the time you've got it into a nice form, you've got some nice results that you want to be able to share, you write up a paper, then that journal paper submission is out of the way, great, breathe a sigh of relief, carry on with your research, fix some bugs, develop your techniques a bit more, then the review comes back and says, oh yes, we really liked it, but can you zoom in on the 100 to 130 hertz region? Yes, we thought that it would work better if you tried a different sound. So yes, what about how much is that dog in the window? I think that would that'd be a really interesting result to see. And so how can you actually go back to where you were 6 months ago when everything else has moved on, and know that you can just push a button, make very minor modifications, and then very quickly and easily produce what has been asked of you? So I want to introduce a very slightly different definition of an experiment here. I would say that it's a well-defined activity that is intended to generate a reproducible result. So as a corollary of that, I would define research, or maybe a research career, is formed of a natural progression of such experiments. So not only does this include the classical scientific method of establish a hypothesis, do the experiment, draw a conclusion, but also all those related activities, like producing graphs for journal papers, producing a particular audio output, signal reconstruction, anything like this which draws on the results of previous experiments. I would say try and think of those also as an experiment. Because one thing that we can do is enumerate these so that you've actually got a chronology of a particular research timeline for a particular project. And you say, well, experiment 1, I start out by analysing one of these existing methods in the literature. By the time I've got onto experiment 2, I've developed my own idea, I want to try it out, see whether it's got promise. Experiment 3, you're getting more confident it's shown its worth. you're now able to refine it and compare it with the original, at which point you think, right, I'm ready to present this to a slightly wider audience in my seminar. So the act of producing graphs and all that audio output, you would say, call that an experiment. So you have a script, experiment 4, which actually goes through and produces all those things. So that way, when the time comes that your journal paper review comes back and they want you to recreate the graphs, you have a nice potted script that does it, and you're not having to go back and pull together, run this experiment, run this one, save this graph to here, do that. We want to try and improve the flow of these things and actually make it easier on yourself. So your experimental objective either would be your classical scientific method hypothesis that you want to test, or your intention is that there's something some specific form of output that you're intending to generate. So if we look at what goes into an experiment, or how an experiment is defined, I would say that the source data going in, you have to specify where your data is coming from. Otherwise we have the problems, as Mark alluded to earlier, that the data that you've referred to is something that you don't have the rights to publish. So your data might be a particular known corpus of musical works or audio source data, or it might be something you've generated yourself. But from a software point of view, I would also define a generator. Because in a lot of signal processing methods, quite often the way that you'll develop your work is that you start off by saying, here's a method, let's try it with a mixture of sinusoids in a certain level of Gaussian noise. Yes, that works, great, let's try it on synthetic data. And so you define a generator as well, and your generator then will be a function that takes number of parameters to say how many sinusoids, how much noise, and so on. And that is a key part of the experiment. And if you've got something that can generate data on demand, then that improves your repeatability. The algorithm in the middle, obviously, the key distinction here, though, is that it's the implementation of your algorithm at a particular point in time. You've written up that journal paper, 6 months have passed, you've actually changed the bit in the middle. You can't rely on running that previous experiment again and getting the same results out, because things have moved on. So we'll talk about version control and how that attacks that point in a moment. And then the final part of the experiment is what you're intending to get out of it. Because if your experimental script, you can just run it and then it produces everything, all your graphs, then there's no messing around afterwards, faffing around to the nth degree to just tweak things here and there. You've got a nice turnkey system, run the experiment, grab the data, produce nice formatted output. So when you code up the experiment, I like to prefer to have one single application or script, depending on which programming language you're using, for each experiment. And Chris talked about the workshops on how you can store all your source and organise it in directories. And so, reflecting that, I think that a nice idea is you have your core library with all your different algorithms inside it, and then the actual experimental scripts or applications are actually very thin wrappers that just grab bits here and there, grab the data from here, do this bit of setup, run this algorithm here with these set of parameters, the output is going to go through this particular renderer and so on. And so by having them as separate scripts, it means that you can keep them knocking around, you can save a backup of them, and if you're needing to then compare experiment 12 with experiment 11, you've actually got a nice quick way of doing it because you've got something that shows how things were at that point in time. So the experimental script as well needs to do several things, such as setting up the environment. As was mentioned before, there's lots of papers where the instructions for reproducing someone else's previous experiment was so complicated that it takes a year, 18 months to get around it. If you want someone to be able to reuse your code, you don't want to have 3 pages of documentation on what they need to do to set it up. So the script must try and do as much setting up as possible so that you've got a real turnkey solution. Press the button and go. So automation really is everything. As much as you can get that is run by a script, then the better. I'll kind of skip this most. I think what he talked about IPython, I think that could be a very interesting development. I've noticed a few people in research seem to be using that. Okay, version control, very briefly. Show of hands, how many people here are using version control at the minute? Oh, okay, that's good. We're preaching to the choir somewhat. So, okay, I can probably skip most of this in that case. I'd say that the useful point about version control is not only that you've got the elements of backup, but also you've got checkpointing. As soon as you've reached a point where something works, check it in. Check in early and often. That's kind of quite a core software engineering paradigm. As soon as something breaks, you've then got a nice, easy way of going back and doing a bisection to work out which version it was that broke anything. There are holy wars about version control. Doesn't really matter. Pick whatever does the job. Subversion is the simplest. If there's all this set up with Mercurial, go for that. Now, branching and tagging. If you've got this situation then where you need to go back to your to what you were doing 6 months ago when your journal paper was published, what you would do is you create symbolic tags all the way through, and then on your experiment 6 tag you would then check out a new source working copy with all that data in, and then at that point you can apply any changes that you need to make that the publishers have, or reviewers have asked for, and you can carry on working along a branch. If there's any bug fixes that you make, you can then merge that back into your main line. So very, very briefly, unit testing is something that I wish I'd discovered 10, 15 years ago. It would have taken months of my PhD if I had. Because ultimately, you want to spend your time doing research and not debugging. Debugging is expensive. If by the time you've put together your system of all these nice components that you built up, you then discover that there's a bug in your FIR filtering routine, really what will happen is that you'll see it at the top level. There's a particular data case you put in, it doesn't work. It works for everything else. And so the process of hunting the bug down the system until you discover that there's a little problem in your FIR filtering routine is very expensive, and you'll waste weeks or months on it. So avoid that by embracing unit testing. So really it's just about breaking all these components into small boxes and testing for any set of inputs, what's the output you expect, and forcing you to think about the boundary conditions, the awkward cases, what happens if you put in 0, what happens if your data isn't padded or a factor of 2, and so on. And we talked about reproducibility in terms of running on different platforms, and this is really useful if you've got something that works in C++, say, on Windows, someone else wants to run it on a Mac, or a 32-bit has to be ported to 64-bit. As soon as you've got all those level components unit tested, it can give you much more confidence that it will work, because you can test each layer of the system, test those awkward cases, and you'll run into fewer problems later on, and your code will be more usable by everyone, really. So just how to do it, pick a framework. Really it depends on which language you're using. They're all called something unit. Break things down into the smallest parts that you can, because in terms of value for money, the smaller parts that are used by everything else, your FIR filtering, your FFTs, those are the ones to concentrate on. And if you're really keen, as Cameron mentioned, set up a Hudson continuous integration environment. Every time you make a change, everything reruns. This is what we do in our company. Any change that gets checked in, all the unit tests rerun, everything gets rebuilt several times a day. So I'll skip that. So yeah, three things you can do. Enumerate experiments. Think about what each experiment is actually aiming to do. Get everything into a version control, and it seems like the Easy Mercurial thing is a great way to go on the SoundSoftware site. And try and attack unit testing of your lower level components, because you'll get a lot of value from that, and you'll spend a lot less time debugging. Okay, thank you.